So those are the three links of the manipulator. And if the manipulator is to do something useful, you perhaps want to put a gripper in the end. We'll not show the gripper. It's just something which we need later on. But you could have a gripper which will maybe use to grasp an object. So in this case, there's a convention used to determine angles. Theta 1 is the angle made with the horizontal. Theta 2 is actually the angle made by the first link with the second one. It's a relative angle. This is the way it is shown. It's clockwise, so it's negative theta 2. And then this would be positive theta 3 because it's counterclockwise. So this point, right now I put an object, but this is actually the end effector. Let's say that the coordinates of the end effector will fix an axis. Say the axes are x, y, and so the position of the end effector is xe, ye. So here is the forward kinematics, the definition of forward kinematics. Definition of forward kinematics. Okay, so given the joint angles, that would be theta 1, theta 2, theta 3. Compute the position and orientation of the end effector. In fact, you can compute the position of any point on the manipulator. Just that happens that we are usually interested in putting the end effector at the location where we want to pick things. That's why it's usually the end effector. But that's the definition. Now I forgot to draw the orientation. In this case, the orientation for the end effector is going to be the angle made by the end effector with the world frame. So let me move this. So this theta is unknown, this xcy is unknown. So position is xcy, orientation is theta. Right? Theta is both things. For a two-dimension problem, we're only interested in three numbers: the position, which will be two numbers, xcy, and orientation theta. In three dimensions, this will become more complicated. We'll have three numbers for the position and three numbers for the orientation with respect to x, y, and z axis. Okay, so now what we'll do is I'll show you how to set this up. It turns out that with our homogeneous transformation we've looked before, this process becomes extremely simple, provided you specify the axis in the right way. Okay, and before I get to using homogeneous transformation, this particular problem can be done by just trig. You don't really need to do any homogeneous transformation. So let me just do the trig first and solve this without using any homogeneous transformation. And that can sort of help you to get intuition to do it with homogeneous transformation, which is more generalizable to 3 dimensions. So what I'm going to show you is probably restricted to 2 dimensions. So what we'll do is we'll use trig to do this. So method one, just simply trigonometry. So in the trigonometric method, what you'll do is you'll show the angles with in a non-zero position first. So I'm showing it this way because the way I've shown it, all the angles comes out to be positive. So this is, for example, theta 1. This is theta 2. It's positive because it's counterclockwise. Theta 3. And then it is not too hard to see that the angle made by the second link, the blue link, with respect to the horizontal is just simply the sum of the two angles, theta 1 plus theta 2. And this angle is going to be just theta 1 plus theta 2 plus theta 3. Let's put down some distances. So let's say that this is L1, it's L2, it's L3. And then, of course, our coordinate axes are this. And then, of course, we're trying to compute the position of this point E. So we can put some names O, P, Q, and E. Okay, so with this sort of drawing, which is, I would say, fairly detailed, we can figure out what XCY is, just taking the X and Y component of X and Y. So what I would do here is I would just drop perpendiculars. This is XC, and then this is YE. And so it's not hard to see that XC will be L1 cosine theta 1 plus L2 cosine theta 1 plus theta 2 plus L3 cosine theta 1 plus theta 2 plus theta 3, right? And then YE is L1 sine theta 1 plus L2 sine theta 1 plus theta 2 plus L3 sine theta 1 plus theta 2 plus theta 3. And then the orientation. So these are the positions. So orientation, we just put it here. So simply the net angle of the end effector is going to be theta 1 plus theta 2 plus theta 3. Okay, this is perhaps how you would do it if you did not know anything about homogeneous transformation. Now, in this case, it's fairly straightforward to do it by trigonometry, provided you draw that figure in that fashion. Now, let's redo the same problem using homogeneous transformation with the hope that what we'll get will be the same as what we get using trigonometry, which we know is correct based on our reasoning. And then when we go to 3D, we'll never look at trigonometry. We'll just go with homogeneous transformation. Okay, so here is method 2. Okay, in this case, what I'll do is I'll just draw the links in the in the position where theta is all 0. So here we have the 3 links in the position where all the angles are 0. Once we have that, we're going to put coordinate frames. So x1, y1, x2, y2, and x3, y3. All of these frames are now along uh, the links that's shown. X0, y0 is also here. So I'm just going to write y0, comma, x0, x1. And then note that the z plane, the z axis sticks out of the plane. So z is going to be this way. This is going to be z0 or z1. This will be z2, z3. So when the manipulator moves, that is, the angles changes, z0, it's going to effectively spin like this, right? So it's going to move that way, and then that will move and so on. So motion is in that plane. Okay, so we've defined the frames, and that's what we need in order to define the homogeneous transformation. So first, h1 with respect to 0. So this is how frame 1 will move with respect to frame 0. So if you remember, we had written down this 4x4 matrix, which consists of a rotation matrix and then the translational piece. So this is O10 with a different color. O21, O32, and then let's define the end effector here. Okay, so the rotation matrix is cosine. I can use this, right? C1, S1, S1, C1, 0, 0, 0, 0, 1. That's the rotation matrix. And then I need to put the origin O10, that will be 0, 0, 0. And then these are placeholders. Okay, so what I have written down is this piece is the rotation matrix of 1 with respect to 0. It's simply RZ by an angle theta 1, where C1 is cosine theta 1, S1 is sine theta 1. And then this piece, this should be 1, is O10. So O10, you can see it is stuck to the origin. So it's going to be 0, 0, 0. Okay, similarly, we can write H21. It's going to be C2, S2, S2, C2, 0, 0, 0, 0, 1, 0, 0, 0, 1. Okay, next I need to write the position of O21. So this is the frame, this frame, the origin of this frame. And what I'll do is I've used L1 to be the distance from this point to that point. So that's going to be simply L1, 0, 1, 0, 0. So this piece is R21. This piece is O21. Again, we can note that it's L1 because the distance is along X is L1. And then it's the Y distance and Z distance is 0. So it's 0, 0. And just note that it's a local distance, the distance of O21 with respect to the first frame, O10. Okay, the last, we need two more. One more, sorry, for 3. cosine theta 2. Okay, same logic. Then 0, 0, 0, 1. Okay, now we need to write the position of O3 with respect to frame 2 with respect to the previous frame. So the local distance. We know that the distance is L2. So I'll write just L2, 0, 0. The L2 is because that's just the local distance. We are finding the local distance because this is all 3 with respect to 2, right? So this is R32. This piece is O32. C3 is cosine theta 3. Another length which I wrote down here is L3. So note that L3 doesn't really show up, but it will show up soon. So that's the homogeneous transformation. Now what we need to do is, our goal is obviously to find the position of point E. So how do we get that? This is how you'll get the position of point 3. We take this. Okay, so I need the position of the end effector in frame 0. Okay, the way you do that is that's simply H30 E in frame 3. Okay, so this note that this is frame 3, the position of this point in this frame. So you can see that the position of, write this down. So this would be, by the way, H30 is H10, H21, H32. This is something we've derived in the past, right? If you have successive frames, then you just take the multiplication in that order, and that gives you H30. Now E30 is the position of E in frame 3. So you can see that the position of this point with respect to this frame is just L3, 0, 0, and then the 1 is a placeholder. Okay, so you have to use the H's from the previous page, and then just keep sort of multiply them, and if you simplify, you'll get something like this: C123 minus S123, S123, C123, 0, 0, 0, 0, 1, and 0, 0, 0. And then over here, you'll get L1 C1 plus L2 C12, L1 S1 plus L2 S12 0, 1. And then we'll just keep the L3 as is. Okay, so that's what comes out. And then if you want to find the position of E0, what you'll do is you'll do the multiplication, and what will come out from that is easy to see. It's going to be so L3 times this, and then 0, 0, and then 1. So what you get is this: L1 C1 plus L2 C12 plus L3 C123, L1 S1 plus L2 S12 S123, and then 0, and then 1 is a placeholder. S123 is sine theta 1 plus theta 2 plus theta 3. C123 is cosine theta 1 plus theta 2 plus theta 3. And so if you look at this expression for E 0, it's nothing but xe, ye, 0, 1. So this is xe. So if we go back and try this with our trig expression, is exactly what we got. L1, C1, L2, C1, 2, L3, C1, 2, 3. And then if you look at the other one, y, it's L1, S1 plus L2, S1, 2, L3, S1, 3 is L1, S1, L2. Okay, so that's that. So that agrees with that formula, but we also need the orientation. The orientation is actually easy to see from here. This represents a rotation of 3 with respect to 0, right? But that is basically rotation about z-axis with an angle θ1 plus θ2 plus θ3. So this is the orientation, θ1 plus θ2 plus θ3 with respect to the horizontal, which is exactly what we got here. It's θ1 plus θ2 plus θ3. So same thing.